Saturn hangs in the night sky right now, visible on the right night with nothing more than a pair of binoculars. You can see the rings, you can see the tilt. It looks close enough to touch. And that accessibility, that casual visibility from your backyard, creates one of the most dangerous illusions in all of human ambition. Because Saturn is not close. Saturn is not reachable. And anyone who made the journey there, with every technology we currently possess or could realistically develop in the next several decades, would not be coming back. Not because of bad luck, not because of insufficient funding, because the universe has rules, and those rules do not negotiate. Let's establish what we're actually talking about. Saturn is the sixth planet from the Sun, orbiting at an average distance of roughly 1.4 billion kilometers from Earth. That number is so large it collapses into meaninglessness the moment you read it, so consider this instead. The International Space Station orbits about 400 kilometers above your head. Saturn is 3.5 million times farther away than that. If you drove a car at highway speed, without stopping, without sleeping, directly towards Saturn, you would arrive in approximately 1,700 years. This is not a distant star. This is not another galaxy. This is our own solar system, and it is already so large that the numbers beg our imagination. Mission planners have run serious calculations on crewed Saturn missions. The results don't inspire confidence. They inspire a particular kind of dread, reserved for problems with no solution. The dream exists, and it deserves acknowledgement. Saturn is one of the most visually spectacular objects in the known universe. Those rings, made of ice and rock, spanning 282,000 kilometers, are a sight that has captivated astronomers since Galileo first squinted at them through a crude lens in 1610. We have sent probes, we stared through Hubble. And every image makes the pull stronger. Astronauts and engineers and dreamers look at Saturn and think, what if we could actually go there? What if a human being could orbit that planet, watch those rings catch sunlight in real time, and radio home with a description no camera could fully capture? It is a beautiful dream. It is a dream worth having. It is also a dream that collides at every single angle with physical reality. The first collision is time. Getting to Saturn is not a matter of pointing a rocket and firing. Planetary trajectories require what engineers call gravity assists, slingshot maneuvers around other planets to build up speed without burning impossible amounts of fuel. The Cassini probe, one of the most sophisticated spacecraft ever built, used gravity assists around Venus twice, Earth once, and Jupiter once before it reached Saturn. It still took 6 years and 9 months. Cassini had no crew. It needed no food, no water, no oxygen, no psychological support, no exercise equipment, no medical supplies, no radiation shelter. It was a machine, and it still took nearly 7 years. A crewed mission, carrying everything humans need to survive, would be heavier, which means slower, or would require so much fuel that the rocket equation breaks down entirely. Realistic estimates for a crewed Saturn transit sit between 3 and 6 years one way. That is 3 to 6 years of continuous spaceflight before you even arrive, and then you have to come home. Here is where the second wall appears, and it is not made of metal or distance. It is made of particles you cannot see, cannot feel, and cannot stop. Beyond Mars, the Sun's magnetic field, the heliosphere, weakens considerably. It acts as a partial shield against galactic cosmic rays, which are high-energy particles accelerated to near light speed by distant supernovae and other violent cosmic events. Inside Earth's magnetosphere, you are protected. On the ISS, you receive some protection. On a 6-year journey to Saturn and back, you are exposed. Galactic cosmic rays do not care about spacecraft walls. Aluminum, the standard material for spacecraft hulls, actually makes the problem worse in some cases, because when these particles strike metal, they produce secondary radiation that is itself damaging. The particles pass through you, they pass through your DNA, they break chemical bonds, they cause double-strand breaks in the double helix, the kind of damage that leads to mutations, to malfunctioning cells, to cancer. NASA's own estimates suggest that a Mars mission, far shorter than a Saturn mission, would expose astronauts to radiation doses approaching career limits. Saturn multiplies that exposure by a factor that, under current shielding technology, is simply incompatible with long-term survival, and that is before accounting for solar particle events, sudden bursts of radiation from solar flares that can spike exposure dramatically within hours. But the radiation is only what is happening to you. Your DNA. Something else is happening to everything else. In microgravity, the human body begins to dismantle itself with quiet efficiency. Bones lose density at a rate of 1 to 2% per month because the skeletal system has no weight to support and interprets this as a signal that it is no longer needed. Astronauts returning from 6-month ISS missions show bone density losses comparable to someone decades older. Their risk of fractures during the physical stress of re-entry and landing is measurably elevated. A 3-year outbound journey to Saturn means somewhere between 36 and 72% cumulative bone density loss if countermeasures fail or prove insufficient. Your femur, your spine, your hips become structurally compromised. Exercise regimens on the ISS slow this process but do not stop it, and exercise requires time, equipment that can break, and a crew that is not already weakened by radiation fatigue. Meanwhile, the heart, which is a muscle, shrinks. In microgravity, the cardiovascular system does not need to pump blood against gravity, and it adapts accordingly. The heart becomes smaller and weaker. Blood redistributes toward the upper body, causing chronic facial swelling and placing pressure on the optic nerves. Studies of long-duration astronauts have found structural changes to the eye itself, the eyeball flattening slightly, the optic nerve developing sheaths of excess fluid. Some astronauts return with permanent vision impairment. On a Saturn mission lasting the better part of a decade, these are not risks, they are near certainties. And the problems do not exist in isolation. They compound. Radiation damages DNA, but it also damages electronics. Spacecraft systems exposed to deep space radiation for years accumulate bit flip errors, sensor degradation, and component failures at rates that increase non-linearly over time. Micrometeorite impacts, statistically negligible over short missions, become a numbers game over years. The outer solar system is not empty. It is filled with debris, dust, and particles that at orbital velocities carry the impact energy of bullets. A small breach in a pressurized hull on a 6-year mission, 800 million kilometers from the nearest repair facility, is a different category of problem than a small breach on the ISS, where evacuation is 90 minutes away. At Saturn, there is no evacuation, there is no rescue. Mission Control's voice takes 83 minutes to reach you one way, meaning that any emergency requiring real-time guidance is an emergency you are solving alone, with whatever crew and resources you have on hand, while your crew is physiologically compromised, while your systems are aging, while the margin for error is functionally zero. Life support systems, which must cycle water, scrub carbon dioxide, regulate pressure, and maintain temperature, are mechanical systems, and mechanical systems fail. Every additional month in space multiplies the probability that something critical breaks in a way that cannot be fixed with available spare parts. These systems were not designed to run for a decade without servicing. Nothing we have ever built was ours, as designed for that. The conclusion is not a matter of perspective or pessimism, it is the output of a calculation that aerospace engineers, biologists, physicists, and mission planners have run repeatedly and arrived at the same place. A crewed Saturn mission and return, with current propulsion technology, current radiation shielding, current life support systems, and current medical understanding of long-duration spaceflight, is not survivable. The compounding of transit time, radiation exposure, biological degradation, system failure probability, and the complete absence of any rescue or resupply option creates a scenario where the question is not whether something will go fatally wrong, but which of the many simultaneous failure modes reaches critical threshold first. Distance alone would be enough to make it essentially impossible. The biology alone would be enough. The radiation alone would be enough. The fact that all three exist together, reinforcing each other, is not a solvable engineering problem under known physics. It is the universe telling us, in the clearest language available, that this particular journey is not for biological creatures with lifespans measured in decades. What we have managed to do is something arguably more extraordinary. Cassini, launched in 1997, spent 13 years orbiting Saturn. It photographed hurricanes at Saturn's north pole spanning the diameter of Earth. It discovered geysers of water vapor erupting from the moon Enceladus, raising serious questions about life in that moon's subsurface ocean. It mapped Titan's hydrocarbon lakes. It sent back images of a ringed planet so stunning they look fabricated, and it did all of this without a single human life. We sent our curiosity there, encased in metal and software, and it worked. Our instruments have touched Saturn. Our mathematics have described every ripple in those rings. We may not be able to go there in person, not with these bodies, not in these lifetimes, and perhaps not ever. But we have seen it. We have measured it. We have, in every meaningful scientific sense, explored it. The cosmos is not waiting for us to catch up. But the fact that a species of primates, on a pale rock orbiting an ordinary star, managed to build something that reached Saturn at all is not a small thing. It is, in its own way, enough